Okay, another type of reaction we're going to look at is called double displacement. And you'll notice that that displacement or that replacement word, that means things are trading places. Okay, one thing is kicking something else out and taking its spot. But double displacement is different in that nothing is alone. Okay, in our previous example, aluminum was by itself or iron was by itself. In this case, all metals have a partner. And remember, positives always attract to negatives. The biggest thing here is that opposites attract. Two negatives will not attract to each other. They repel. Same with two positives. You have to put opposites together. So here we have two different compounds. Let's take a look at this on the board before we do it in front of you. Lead 2 nitrate and sodium iodide. Now this looks a lot like single displacement. When I put those together, the lead wants to go in and take the place of the sodium, and when it kicks the sodium out, the sodium goes back and takes the place of where the lead was. Nothing is left by itself. They all have a partner, but when this new combination is formed, we see a change happen. So my products would be lead is going to combine with the iodide. So I would write lead 2 iodide, okay? And then sodium is going to go with the nitrate. Sodium is going to combine with nitrate. I'm just going to write that combination. And now the goal is to write the correct formulas for these. Okay, it's all based on what those charges are. How many of one will combine with another based on electrons that get transferred from one thing to the next. So let's first take a look at lead 2 nitrate without paying attention to any of this stuff over here. Lead has a charge of +2. Nitrate, if you look it up on the back of your periodic table, is one of those groupings, and it is a -1. So I'm going to need 2 nitrates to go with 1 lead. Pb and 2 nitrates, and remember nitrate is this combination that is NO3. That won't change. That's always nitrate. There's lead 2 nitrate. Now we go to our next one. Sodium iodide. Look it up on the front of your periodic table. You see IDE. We're talking about a single element. Sodium is a +1. Iodide's a -1. So that's a perfect ratio, 1 to 1. I don't need more of one. So this is NaI. Now, here's the part where most people have a tendency to want to go off track. This little 2 down here was because of the charge on lead. I'm not going to just automatically take that over with me. I need to see what's there. The new combinations will form based on their charges. Lead is a +2. Iodide, I've already looked it up, is a -1. So in this case, when they form, a lead's going to need 2 iodides to make a neutral compound. So this would be PbI2. Well, Mr. Throne, there's no 2 with this I. Yep, we'll take care of the amounts when we get to the end. But this is how that has to form. They're going to attract until they have that ratio, and that's when everything sort of neutralizes or cancels each other out. Take a look at sodium nitrate. Sodium's a +1. Nitrate's a -1. Here's a perfect combination. Those are going to go together in a 1-to-1 ratio. Na and then a single nitrate. But remember, nitrate is NO3. It's that whole combination. There's just one of those combinations. Now when I look at this, there's obviously some things that jump out at me. There's 2 iodines here, but there isn't on this side. I can't put a little 2 down in this, because if I do, that makes something that's not possible. That's not the formula for sodium iodide. So I have to put a 2 out front. Those are physically connected. If I want twice as much iodine, I'm going to need twice as much sodium as well. Well, I got to take care of that over here. I'm going to need twice as much sodium on this side, so the sodiums are balanced. And then I look and go, wait, that's 2 nitrates, because that distributes to everything, but I have 2 nitrates over there. See how those fit? That's not an accident, that's chemistry. 1 lead, 1 lead. Everything should fit together like a nice puzzle at the end. That's an example of a double displacement reaction. Now in real life, most of the time when we see these reactions, the way we get them to happen is we dissolve them all in water. We do what's called a solution reaction. We put them all in a solution. So I've got these 2 solutions down here. I've got lead nitrate and sodium iodide. And you notice they both look kind of just like clear solutions. They look like water. This one's a little on the cloudy side, but not much. But all those ions are dissolved and they're floating around in there. And that's the activation. They're either moving around already, separated from each other, and they're just waiting to recombine in a different way. So I'm going to show you what this looks like. I'm going to add in some sodium iodide. And you may recognize the outcome of this once you see it, because we've done some similar things in the lab. It's just you got to do it virtually this year instead of in front of you. Now, I'm going to add this other solution of lead nitrate, and when I do, those atoms have a tendency, or those ions have a tendency to want to combine together in a certain way, and you'll see the product form. Ooh, all of a sudden we see that dark yellow stuff just show up out of nowhere. What the heck is that? Okay. And I want to show you that there's really two things in here. This is something that's hard to see right now, but if I were to put this in a centrifuge and spin it around really, really fast, it'd be like the gravitron. It would pull all that heavy yellow stuff to the bottom, and we would have a nice clear liquid on top. And there's really two things in that. The yellow stuff happens to be lead iodide. It's what we call a precipitate. And this is what most double displacement reactions look like. Two solutions go together. They make this solid, gooey stuff. In this case, it's yellow. And then there's a clear solution left over afterwards, too. So what happens to be that sodium nitrate is still dissolved in water and you can't really see it, but the lead iodide sticks together as this heavy stuff and it kind of sinks down to the bottom. Almost all double displacement type reactions will have this same look. Two solutions that produce a solid precipitate. And that's double displacement.